Swayam Prabha. Digital India. Educated India.
Okay, so good morning everyone. So we were looking at the natural proof barrier result due to Rasborov and Rudick, and what we showed that under the assumption of this lemma we can actually prove that there does not exist any natural proof separating NP from P/poly unless you can break one-way functions. Okay, and what this lemma says is basically that well, if one can break a pseudo-random function generator, okay, so this is basically a pseudo-random function generator. So basically one can distinguish between a function that is truly random versus a function that is drawn from the distribution psi y. Okay, then one can actually break a pseudo-random generator. Okay, so phi is a pseudo-random generator. One can show that its hardness is also bounded. Okay, so breaking a pseudo-random function generator gives one a way to break a pseudo-random generator as well. Okay, so that is the intuition. I can just write it over here. So implies one can break a pseudo-random generator. So this is roughly the intuition. So now let's look at the proof. So just let me recall what this distribution psi y was. So we have this function phi. Okay, we can think of breaking the output of phi into two parts. Okay, so we can think of breaking phi of y as phi 0, phi 1 of y. And now given any x belonging to 0, 1 to the power n, depending, and let's say that x is equal to x1 up to xn, what I can do is I can build this function psi xy, that is, we can think of it as being indexed on x now as psi n composed with psi xn. So look at the or we can look at it from this side. So let's say psi x1 of y, compose that with psi x2 and so on up to psi xn. So this gives us a k-bit string. Okay, and now we can just define psi y. So if y is chosen randomly, so with respect to y, I can define this to be a map from 0, 1 to the power n to 0, 1. So essentially what we do here is that not just we take this string, but we take the first bit of this string. Okay, so this basically gives us a map from x comma y to 0, 1. That is how we defined it. So now this gives us a distribution over functions. So I can choose a distribution, I choose y randomly, and this gives us a way to choose a function from distribution. And now what we are saying is that if I can distinguish between these two functions, then I can break a PRG phi. Okay, so let's look at the proof of the lemma. So first what we will do is we will construct a tree. Okay, so let B of n be the set of all binary strings of length at most n. Okay. So what is the cardinality of B of n? So B of n will have 2 to the power n plus 1 minus 1 many strings, right. So now corresponding, so we'll build a complete binary tree of depth n, each of whose nodes will correspond to one binary string. Okay. So if I have a complete binary tree of depth n, it has this many nodes. Okay. So the number of leaf nodes is 2 to the power n. So each of my leaf nodes will correspond to a binary string of length n, and the internal nodes will correspond to binary string of length less than n. Okay. So it is built in a very I mean in the most natural manner. How do we define it? So we build a binary tree T corresponding to Bn. So the root of T corresponds to the empty string. Okay, let's call it I have used epsilon. Okay, I have not used epsilon. Okay, corresponds to the empty string epsilon, and if a node corresponds to the string sigma, then its left and right children correspond to sigma 0 and sigma 1 respectively. Okay. So just as an example, if let's say n equals 3, what do we have? So we have epsilon at the root, then we have node corresponding to the strings 0 and 1, then we have nodes corresponding to 0 0 0 1, 1 0 1 1, then we have 0 0 0 0 0 1, 0 1 0 0 1 1, 1 0 0 1 0 1, and 1 1 0 1 1 1. So this is my tree T. Now what we will do is that we will define a probability distribution. Okay, so yeah, So we will also define randomly 2 to the power n subtrees of T as follows. Okay. So T1 is just the subtree which consists of only the root node. Okay. And Ti plus 1 I will define as follows. So for a random node sigma at depth less than n in Ti, add the two children sigma 0 and sigma 1 to Ti. Okay. So what you do is essentially that take Ti, take any random node sigma in Ti that is at a height less than n, strictly less than n. Now you just randomly add its two children, and that is my Ti plus 1. Okay. So once again we can look at an example just to familiarize ourselves. So we have this as T0, then in T0 there is only one node, so T1 has to be this tree. Okay, now T2, I randomly pick one of these two, so not just a random node but for a random leaf node. Okay, so yeah, in a internal node of course you cannot add any children. For a random leaf node at depth less than n. Okay, so between these two leaves I pick any one. So let's say I pick this guy and I add its two children 0 0 0 1. This becomes my T2. Sorry, I start with T1. This is my T2. This becomes T3. Then let's say 0 1. I pick this one. This is also at less than height 8. So I pick this one. I add 0 1 0 0 1 1. This becomes T4. Now I pick this guy. So we have this 0 1 and I have something over here. Now I add its two children here 1 0 1 1 T5. Now let's say I add children to this guy. So this is 0 0 0 0 0 1. This is my T6. And now let's say that T7 is, I mean, you pick any one of these two, that is T7, and the last one will be T8. Okay, so I'll just okay, so this is how I get a sequence of trees T1 up to T to the power 2n. Okay. So now I will use these trees to define distributions over functions. So corresponding to each tree Ti, I will define a distribution. Okay. So now corresponding to each Ti, we define a distribution over functions from 0 1 to the power n to 0 1. Okay. So how do we define the distribution? So let's take a Ti. Okay. So consider some arbitrary Ti. Now for x belonging to 0 1 to the power n, what we will do is we will look at the tree and we will look at so now note that each node x is basically a leaf node in t to the power n. Okay. Now Ti might not have that leaf. Okay. So I will look at the maximum common segment between x and Ti. Okay. So I will look at what is the maximum m, okay, that I can go to, which is common to both Ti and x. Okay. So in other words, let m be the largest integer such that x1 up to xm. So this string is a node in Ti. Okay. So for example, okay, let's take an example here. Suppose my x is, or suppose my Ti is, or Ti, suppose I equal to 5. Okay, and x is the node, or x is the string 101. Okay. Then what is m? So look at T5. Okay, look at where 101 is. So basically I can, if I actually trace 101, I only go up to depth 2. Okay, so in this case, so then m will be equal to 2 in this case. Right. Now of course the minimum that m can be 0 and the maximum that m can be is equal to n. Let y be a string chosen randomly from 0 1 to the power k, and now I define the function psi I y of x as follows. So essentially what this function will be is, it will be okay, so I have erased it. So it will be similar to psi y, but after this x. Okay, so whatever is the common part, so that common part, for that common part I will use my tree T, and after that I will basically be composing the function phi. Okay, so essentially this will be phi xn composed with phi xn minus 1 up to phi x m plus 1 of y, and of course I take the first digit of this. So the first bit of this. Okay. So note what we are doing. So till m, okay, so till m basically I have my tree Ti. Okay. After that I am using the function phi to get the value of psi iy. Okay. And of course, so we have to look at one condition. So if, what if m is equal to n? So if m is equal to n, then I don't have m plus 1. So we'll define it. So if m equal to n, okay, then just output the first bit of y. Okay, whatever is the first bit, you just output that. So now let's try to understand what these functions are doing. So what happens if I equal to 1? Okay. So that is if my tree is just the empty node or the empty string. So if I is equal to 1, then what is m? M is equal to 0. Exactly. So if I is equal to 1, then m equal to 0. Now what happens if m is equal to 0? What is psi I y of x, or psi 0, psi 1 y of x? I is 1. So it is exactly psi y of x. Okay, because now I am going all the way up from x1. Okay. Okay. The function that we have. On the other hand, if I equal to 2 to the power n, then m will be equal to n, right? And if m is equal to n, then this is essentially choosing a random function. Okay. So if m is equal to n, then what we do is that we just output the first bit. So the function that we are defining, psi two raised to the power n of y. So y is a random string. So this is a random function, fine, chosen uniformly. Okay. Now what is our assumption? So our assumption is that by the assumption of our theorem, what we have is that there exists a polytime computable function A such that if I choose f from this distribution, that is, I randomly choose it from psi y 2 to the power n. Okay. The probability that it accepts minus if I choose a function from psi 1 y is at least 1 over 2 to the power some kn, okay, 2 to the power minus order n. Now, what does this give us? So, essentially what it is telling us is that, well, if I go from 1 psi 1 up to psi 2 to the power n, if I go through all these distributions, then by the time I go from psi 1 up to psi 2 to the power n, there is an algorithm which is able to distinguish between these two functions. Okay. So, now what does that mean is that there exists some I, okay, there exists some I between this. Okay, let me define a notation before that, it will be easier. So, let Pi be the probability that A of f equal to 1 for f chosen from the distribution psi I of y. Okay. So, what this tells us is that there exists an I such that the difference between Pi plus 1 and Pi is at least 2 to the power minus order n, right. So, I mean, this order only has a difference of 1, I mean additive factor of 1 between the constants that is used here and used here, because there are 2 to the power n many of them. So, what we can say is that, well, if for each one of them it is bounded by less than or equal to 2 to the power kn, then by just summing up this will be bounded by 2 to the power k plus 1n. Now, because this is bigger than, let us say, some 2 to the power minus kn, this has to be bigger than 2 to the power minus k plus 1n, something like that, some constant that is changing by 1. Okay. So, there exists an I where this is happening. Now, what is Pi plus 1 and what is Pi over here? Okay. So, Pi, note that, is coming from this distribution. So, this distribution is happening with respect to a tree. Okay. So, a tree Ti and a tree Ti plus 1. How does these two trees differ? Okay. So, let us understand the tree. So, suppose this was my tree Ti. Essentially what it means is that there is some node, leaf node sigma over here. This is a leaf node, and in Ti plus 1 what I have is sigma along with its two children, sigma 0, sigma 1, right. This is exactly the difference between these two trees.